Hey, so penetrator equations is what we're talking about today. Yes, get your chuckles out. It's a funny thing. So the United States has gotten extremely good at having missiles hit the ground and then go like 10 or even 15 meters deep into the ground and then explode, rather than hit the ground and explode when they hit the ground. So we've gotten very good at designing penetrators. And Sandia National Labs in particular has led the way. They've actually started this way back in the 60s, even the 50s. There's a man named, I forgot what his first name is, his last name is Young, but he's sort of the father of penetrator equations, penetrator science, if you will. And he developed all these equations. Basically his job was to go out into the field and collide things with other things, and that's just a cool job in my opinion, but that was his job. I don't know. I would like to shake the man's hand because, well, he's probably dead now, but so that would be gross, that would be awkward. But anyway, so if you want your probe to impact the surface and then bury itself into the surface, this is the video for you. How do you calculate the depth that's going to bury itself? And if you want to define your depth, how do you back out the velocity you need to hit the ground with, okay? So there's two ways to look at this. There's a page in the book about this. I'm not going to list the page number because we change page numbers too often in the Inspires. But the topic at the top says Engineering Analysis Penetrator Equation. There's also on the downloads page, there's going to be a download under the project downloads called the Penetrator Equations. It's a PDF, and it's written by Young, the man, the father of penetrator equations. It's his penetrator equations, and because there's some values in that paper that you're going to need because the values change. Anyway, so the penetrator equation, and there's two equations based on your velocity. Most of our velocities in Inspires, if you're falling from an orbiter, you're going to be above 61 meters per second, which is nice because it's a simpler equation. So let's go ahead. So for so velocities greater than 61 meters a second, this is the equation. I gotta cheat because it's been a long time. So d, the distance that your penetrator goes into the surface, goes into the target, equals 0.1234123 zeros 18 s n times m over a to the 0.7 exponent times v minus 30.5. Now, okay, as you can see, units are going to be all messed up. This equation is for SI units, for metric units. Always use metric in any calculation you ever do. Use metric, okay? You're going to, it's just terrible using English, okay? So D is the depth of penetration. You can look at the page in the book. Mass is the mass of the probe. A is the cross-sectional area of the probe. So as you would guess, a very thin, heavy probe is going to go deeper from this thin, very small cross-section. Like this cross-section is much smaller than this cross-section, right? The cross-section of this marker is much smaller. So imagine this marker weighed like 10 pounds and this thing weighed 10 pounds. Which do you think would go deeper? This one would, because it's a smaller cross-section, like rebar. Rebar is a really small cross-section iron rod, right? It's easy to shove in the ground because it's a real small cross-section, very heavy, okay? So that's what this term says here, is that high mass, low cross-section is what you want to dig into the ground. However, you guys are mass limited, so you can't be too high on mass, right? But it's to the 0.7 power, okay? And then you have V minus 30.5. So you see that if you get below 61 meters a second, this equation begins to break down, right? Because your V gets too close here, especially if V is 30.5, then it becomes 0. This 0 is bothering me. Hang on. So what are S and N? Those are two weird things in this equation. So remember, D is how deep it goes. So here's our ground, and here's the hole we're making. Here's our probe at the bottom, M, and it's got a cross-sectional area of A, and then it went D depth. You like my little drawing here? Okay. So S is the penetrability number. S is called the S number, or S number if you want to be funny. And then N is the nose cone coefficient. Nose cone coefficient. So that basically means that something that with a sharp tip will go on the ground easier than something that's rounded. And so nose cone coefficients, S and N, they're both dimensionless. You can calculate nose cone coefficients, but most nose cones, if you're a sphere, if your object is a sphere, very, very rounded, use a nose cone coefficient of 0.9. If you're so use 0.9 for a sphere. So for a sphere, it's 0.9, and then for something that is has more of a tip to it, so a tip, use 1.0. Okay, that's for nose cone coefficient. There's not many others. There's different kind of nose cones, but nose cone coefficient does not change that much. But it's a 10% change. You can imagine a 10% change in your depth would be a big deal sometimes. So if you have a rounded tip or a sphere, 0.9 is your nose cone coefficient. If you have a sharper tip, like an ogive or just anything sharper than a round, use 1.0 for nose cone coefficient. Now S number is something you're gonna have to look up. S number is one you want to look up in the PDF that's on the Inspires website. I don't have the S number for everything, so I have some S numbers on this sheet of paper. So for dense, dry, cement, or sand, S numbers between 2 and 4. So as the S number increases, your depth increases. So the higher the penetrability it is, the deeper you can go into it. So if you're crashing into a big block of ice, the S number is going to be quite high for that actually. So the S number is 4 to 6 for gravel deposits without cementation, and then 6 to 9 for dense and loose sand. For I don't know what it is off the top of my head for ice, but you can go look it up in the PDF. It's on the downloads page, and you can look up the S number for ice. So basically after that, it's just a plug and chug. You make sure use Excel, okay? Trust me on this one, use Excel, because this is hard to do. Remember, and to do this, just make cells, and then remember the 0.7 to the 0.7 power, you use the caret, and then you do a parentheses 0.7. That's how you do a point to the 0.7 power in Excel, the caret, and then 0.7. If you have trouble with Excel, you can ask us, but put this in Excel, and then you can quickly iterate on, you can quickly change, and you can say, okay, what if we hit the ground at 100 meters per second? How deep do we go? What if we hit the ground at 200 meters per second? How deep do we go? Or you can flip it, and you can say, okay, we want to go so deep, how fast do we have to hit the ground? You got to do some algebra for that. Just so for that, it's just the depth is, so, oh gosh, I can't do that off the top of my head. It'll take me a minute. But you can solve this algebraically. If you want to solve it algebraically for depth, if you want to hit a certain depth, what is your velocity? Let us know if you can't solve it algebraically. You can solve this algebraically. It's not that hard. I just can't do it in front of the on a whiteboard in front of a camera right now. So, but that's it. That's the penetrator equation. It's just one equation, but it tells you a lot. The toughest part is this S number, and then getting this equation to type it in correctly in Excel. That's the hard part too. But if your velocities are too close to 61 meters per second, the equation is going to start to break down. You'll see some weird things happening. But besides that, what's really neat is if you take this equation and you vary your velocity. You say, okay, for a range of velocities, if we hit the ground going this fast, if we hit the ground going anywhere from 100 to 200 meters per second, these are the depths we're going to get to. And you can show how your depth will change. That would be actually very interesting. So, but again, this is if you want to bury yourself. This is the penetrator equation video. If you have any questions, there's a write-up in the book. It just goes over the equation. There's not much to it, it's just one equation, and then you just plug it in and make the values work. Give us a call, give us a call. Send us an email, or you can call us, that's fine too. Email me or PJ or your UAH project manager if you have any questions. Thanks a lot, bye-bye.